So in this video, we will be discussing about a project topic, the impact of climate change on thermal stratification in lakes, which is also a very important aspect of limnology. What is thermal stratification? It is the natural layering of water in lakes driven by temperature differences. During warmer seasons, lakes typically divide into distinct layers: a warmer, lighter surface layer known as epilimnion, a middle layer with rapidly decreasing temperatures called the thermocline, and a colder, denser bottom layer known as hypolimnion. Why is this layering important? This process is crucial because it influences the lake's physical, chemical, and biological dynamics. Thermal stratification affects oxygen distribution, nutrient cycling, and aquatic life, making it a key factor in maintaining the health of these ecosystems. Let's look at how thermal stratification changes with the seasons and its impact on lake ecosystems. In summers, lakes usually undergo stable layering due to temperature differences. The surface water warmed by the sun forms the epilimnion, while the deeper, cooler water forms the hypolimnion. These layers separated by the thermocline, where temperatures drop sharply with depth. Why does this matter? The thermocline acts as a barrier, preventing the mixing of oxygen and nutrients between layers.
When a lake becomes stratified, the mixing between the upper, middle, and lower layer is significantly reduced. This lack of mixing isolates the hypolimnion, the cold and dense bottom layer, from the oxygen-rich surface. Over time, the oxygen in the hypolimnion gets depleted due to a process like organic matter decomposition. Bacteria and other organisms at the bottom break down organic materials, consuming oxygen in the process. Without mixing, no fresh oxygen from the epilimnion can replenish this supply, leading to a condition known as hypoxia. Hypoxia creates a stressful environment for aquatic species that depends on oxygenated waters. Fish and other organisms in the hypolimnion may struggle to survive, especially species that are sensitive to low oxygen levels. These species may be forced to migrate to the upper layers, leading to overcrowding, increased competition for resources, or, in severe cases, death. Hypoxia also impacts benthic organisms, those living at the lake bottom, which are critical for nutrient cycling and ecosystem balance.
While in winters, lakes experience inverse stratification. When lakes freeze, the coldest water, just around 0 degrees Celsius, sits below the ice, while slightly warmer water, around 4 degrees Celsius, settles at the bottom. The ice cover prevents wind from mixing the water, leaving this lake mostly static. This creates a unique environment where fish and other organisms must adapt to low oxygen conditions and reduced movement within the water column, especially in deeper lakes.
Thermal stratification is most noticeable in spring and summer. As the sun heats the surface, the lighter, warmer water remains on top, while the colder, denser water sinks, creating distinct layers. These layers remain relatively stable, preventing mixing of oxygen and nutrients between the surface and bottom of the lake. In fall, cooler air temperature and wind disrupt this layering. The surface cools, becomes denser, and sinks, causing the entire lake to mix in a process called fall turnover. This mixing redistributes oxygen to the bottom and brings nutrients from the hypolimnion to the surface. A similar process occurs in spring after ice melts, when the lake mixes again, resetting its oxygen and nutrient levels and preparing for the summer season. This stratification process is driven by solar radiation, which heats the surface layers and density differences in water, since warmer water is less dense than cooler water. This dynamic plays a critical role in a lake's ecological health, influencing oxygen levels, nutrient cycling, and the habitat availability for aquatic life. Nutrient distribution. Stratification also affects the movement and availability of nutrients. Essential nutrients like phosphorus, nitrogen, often trapped in the hypolimnion, accumulate as organic materials, sinks, and decomposes. While these nutrients can stimulate primarily productivity, they remain inaccessible to the upper layers, or the epilimnion, during the summer months when stratification is strongest. In the epilimnion, nutrient scarcity can limit phytoplankton growth, which forms the base of the aquatic food web. This reduction in productivity impacts the entire ecosystem, including zooplankton and fish that depend on phytoplankton for survival. However, during the fall, when the cooler temperature and wind driven mixing break down the stratification, these trapped nutrients are redistributed throughout the water column. This mixing can be temporarily boost productivity as the nutrients become available for use in epilimnion. While this is beneficial in natural systems, in nutrient-rich lakes, it can lead to problems like harmful algal blooms if excess phosphorus is released. These blooms can deplete oxygen further, creating a cycle of stress for aquatic ecosystems.
Now let's talk about the adaptive measures and mitigation strategies to address the effect of climate change on thermal stratification. In reservoirs and lakes, selective withdrawal systems can be implemented to release water from different depths, controlling the thermal layer and helping mitigate temperature fluctuations that impact ecosystems. Planting trees and vegetation along lake shores can reduce solar heating of shallow areas by providing shade. This slows down warming and maintains cooler water temperatures, minimizing disruptions of thermal layers. Implementing best management practices like buffer strips and reduced fertilizer application can limit nutrient inputs like nitrogen and phosphorus that lead to algal blooms, which increase surface warming and deepen stratification. Installing temperature, oxygen, and nutrient sensors in lake provides real-time data on thermal stratification patterns. This helps in anticipating and addressing issues like hypoxia in deeper waters. Installing aeration or mixing systems can disrupt the thermal stratification and enhance vertical mixing of water layers. This can prevent the formation of oxygen-deprived deep layers by promoting water circulation. By injecting oxygen into the deeper layers of stratified lakes, this method can mitigate the effects of anoxia or oxygen depletion without disrupting thermal layers, thus preserving the stratification while improving water quality. Shifting away from fossil fuels to reduce greenhouse gas emissions can slow the rate of global warming, thus mitigating the intensity of thermal stratification in lakes caused by elevated surface temperatures. Advocating for stronger climate policies that address lake and watershed management can help reduce long-term impacts of climate change on lakes, including enforcing stricter water quality standards and conservation efforts.
A recent study on Ontario lakes has shed light on the effects of warming water temperatures, particularly regarding thermal stratification and its impact on aquatic ecosystems. Research focusing on Lake Simcoe and other Ontario lakes has shown that rising temperatures lead to shifts in stratification patterns. As surface temperature increases, cold water species like lake trout and lake whitefish, which prefer cooler waters, are forced to move deeper to find suitable habitat. This change is tied to the development of thermal stratification, where a stable layer of warm water sits on top of cooler waters, limiting mixing and oxygen availability at depth. For lake trout, warmer water temperature push them out of shallower, more productive zones to deeper, less productive areas, reducing their access to nutrient-rich food sources. This has direct impact on their growth, condition, and reproductive success. The study on over 600 lakes in Ontario revealed that cold water species, including lake trout, experience a reduction in size as lakes warm. In contrast, warm water species like smallmouth, bass, and walleye thrive and grow larger as temperature increases. These shifts in species size and behavior are significant for fisheries management and the broader ecosystem. As cold water fish face challenges in adapting to the altered thermal regimes, there could be long-term implications for biodiversity and the structure of aquatic communities. Understanding these patterns is crucial for managing fisheries and conserving freshwater resources in a warming climate.
In conclusion, the climate change has profoundly altered the thermal stratification patterns in lakes, disrupting their ecological balance and water quality. Rising global temperatures intensify stratification, extending the period of separation between warm surface layers and cooler, deeper waters. This intensifies oxygen depletion in the hypolimnion, threatens aquatic biodiversity, and enhances the risk of harmful algal blooms. To mitigate these effects, adaptive management strategies are essential, including improving water quality management, restoring riparian buffers, and utilizing advanced technologies like artificial mixing systems. Reducing nutrient inputs and carbon emissions are crucial for preserving lake ecosystems in the face of ongoing climate shifts. Ultimately, understanding and addressing the interactions between climate change and thermal stratification is the key to protecting lakes and their biodiversity, ensuring they continue to provide essential ecological, recreational, and economical benefits for the future generations. Thank you everyone for watching and taking the time to engage with this important topic. As we look towards a more sustainable future, it is clear that small actions can lead to big changes. Let's continue to explore and implement solutions that protect our environment and preserve our natural resources. Together, we can make a lasting impact. Thank you again for your time and commitment to sustainability.